we were talking about the do while. So in the case of a for is one of the oldest types of loops, and it has a built-in counter where you have an initial condition. There are three parts in the for. One that is the initial condition, the other one that condition that has to happen in order for the loop to execute, and then just an increment of the initial condition or the step. If we are going to do this, let's just do the same thing. Count through 10 for int x equals 0, which is the initial condition. X less than 10, x plus plus. And if we printed the numbers that x has, it's just essentially going to print all the numbers from 0 through 10. 0 through 9, because it's 10 times when it does the code. One interesting thing here, if we did it like this, which with this plus equals, which you're familiar from last class, it would do it in steps of 2. So you can see how it went from 0 to 4, 6, 8. Again, a for is really useful for when you need to have a counter. And we're gonna learn also today what is an array and why this is really useful for that. I think we should come back to this one because I want to talk about the keyword break and the keyword continue. And to help you understand what break and continue do, let's assume that this is a neighborhood where all these are streets. All the horizontal ones are streets, all the vertical ones are houses. And let's assume that we are an Amazon package delivery person. And this is where we start. And the other restriction of our route is that we can only hold one item. The other restriction is that we can only go line by line. So we cannot go like this around the neighborhood. We have to go in this direction, and then this direction, and then this direction, and this direction, and this direction, and this direction. Let's assume that for the first package, we're going to deliver the package to where the blue X is. And if I was going to do that, just following the restrictions, I would go like this, and then like this, and then like this until I find that blue spot. Let's assume that I give that package, but I can only hold one item. So is it efficient for me to continue going in this direction until I can go back? I don't think anybody would think that it's efficient to continue doing the route when you just found that situation. So a continue allows you to go back to the beginning and then start with the next iteration. Let's make it now yellow for the second iteration. Then the next package is where the yellow X is. So we would go again and continue with the package until we get to this point. A continue would go directly from here to here rather than continuing to do the entire loop until the end. So basically a continue, the statement continue, prevents us from doing unnecessary work, right? Because we're not going through the entire loop to just continue until we finish. So we saved ourselves a little bit of walking around the neighborhood. So then what is a break? The break in the same situation, it also prevents us from doing unnecessary work. Let's assume that we only had one package to deliver. This is our last package of the day. Rather than continuing going through the entire loop like this until we get to the end and we can get to go home, when we're done, we just escape and go home. That's the difference between a continue and a break. A continue will go to the next item on the list or the next item on the loop. A break will completely exit the loop. So let's do this on this 4 just to help you understand. If x less than 4, or when x equals 4, we're going to break. And you're going to see how it does 0, 2, because when it goes into 4, that completely exits the loop. It is not exiting the program, because I can actually do something like this at the very end of the loop, saying loop is done. And now you can see that it goes 0, 2, and then the loop is done. Again, it completely exited the process of the loop that we needed to go through. As opposed to a continue, which a continue, let's say a continue is, in this case, going to go through 0, 2, 6, 8. Why? Because in 4 we said don't print it, just go back to the next item. We are still pending this guy, the slide 11, but we're going to go back to that, because first of all, I want to explain what is an array. So I'm going to go back to my magic whiteboard, and just let's assume that this is our computer memory, where we are going to store some values. And one of the first data structure, actually, let's explain what is a data structure. A data structure is just a way that we have decided to organize data. The most basic situation where we are organizing data is a list, where you have, even let's assume that a shopping list. Let's say eggs, milk, butter, tomatoes. That's, a list. In the very beginnings of computer science, people started realizing that we needed a way to organize data. The very first thing that they figured out was, okay, how do we create a list? How do we represent a list where in the simplest ways? And because memory management at the time was complex, they decided that the best way to represent is to say, where are we going to start storing, or the beginning of the array, how long it is, and what is the data type. Those are the things that define an array. And the main thing is, just in the simplest way, why did the length define that? Because everything in an array has to be next to each other. So it is continuous, and also everything has to be the same data type. That is because we didn't have the ways to efficiently make something a little bit more dynamic. So we needed a way to represent that list. So if we wanted a list of numbers, we would represent it as the int and just curly brackets. But that again meant that all the numbers were going to be next to each other. We were defining that, and we say int x a equals new int, and then we define the length. When we do that, we're saying reserve 5 spaces, 1, 2, 3, 4, 5 spaces for this array called A. And that's where we're going to put our values. So doesn't matter how many values we have, it's going to always be next to each other. That's how the memory management would do it. It would say, just reserve that continuous amount of space. That brings some issues. First of all, once we create the array, because then at some point the memory is going to say, okay, well, I'm going to use all these cells and maybe this one, etc. We cannot just say, if we wanted to grow it, just add one more, because the memory might be used at that point. So if we wanted to add a new member of the array, we needed to grab the same array. Well, we needed to grab that array and then generate a new one. And let's assume that, We just have that extra piece of data that we would have to create a new one that would be the same size plus one more if we wanted to add a new array. So it would be 1, 2, 3, 4, 5, 6. So now this would be the new copy. And let's assume that we had, I don't know, let's say if this was int, and let's just redraw this as int, as a list of 5 arrays, 5 elements. Let's say 6, 8, 5, 12, 13. If we wanted to add, say, number 20 at the end of it, we would have to 6, 8, 5, 12, 13. We would have to reserve the array as a new array, int b equals new int now of 6. And then we would have to copy all the values 6, 8, 5, 12, 13, and then we wanted to add 20 into a new array, and then discard the old one, which would be freeing that memory up. Actually, let's make it a little bit more graphic to really free the memory of that entire array. So then that would be freed up. And that's how we would add numbers to a list, which is a little complicated because it's not dynamic, but also another advantage that an array brings is that because you know where the array begins, in this case it is right here. In this case it's right here where the array begins, and you know the length. If you want to access any of the members in the array, all you have to do is to look for the offset of that array. So if we say B3, essentially means B plus an offset of 3. So it would be 0, 1, 2, 3. In this case, B3 would be worth 12. Again, because we are saying the number of jumps. If we wanted to access the beginning of the list, we would do B0, which points to 6. And so on. Again, these are the number of jumps. Then we go back to the theory. Once an array is declared, you cannot change it in size. We already talked about that and the reasons why. Also, because we are declaring the array and we cannot really change it, everything has to be of the same data type. We can use a creator or an initializer. I'll show you how to use the initializer in a second. And then the creator is a way that we just that I show you on the whiteboard using the keyword new. But there are two things that I want you to consider. One is a shallow copy and the other one is a deep copy. When we talked about growing the array, we were doing a deep copy. That means that we were copying value by value by value. But when we are holding an array, we're not really holding the array. We're only holding the beginning of that array. So if we want to copy that array, it becomes, by default, the default operation is a shallow copy. What is a shallow copy and what is a deep copy? Well, that's a great question. So let's assume that we do int x equals, let's int x. You can put the curly brackets to define it before or after, doesn't matter. Let's say, and this is an initializer of an array when you want to pre-initialize it. And let's use the same numbers that we had defined on our example here, 13, which you can see they're not in particular order. Actually, this element is in a different order than this, but we are reserving 5 elements, right? And then we did int y. If we wanted to copy those values, it is not as simple as doing this. Why? Because if I went, let me just show you one thing actually. Let me put a debug thing here and right click and debug. And once I get to that point, you're going to see that both arrays have the same values, 6, 8, 5, 12, 13. What would happen if I modify on array 1 the second value, or meaning this 8. So if I did, in other words, y 1 equals 25. If I did that, notice that I am only doing it on the y array. In both arrays, it was modified. The reason why that happens is that if we go back to the whiteboard and we are saying that this is our array, right? This is now our array. So I'm going to point to the beginning and say the arrow that is on the red, this is x. And then the blue one is y, and it also points to the same one. That is a shallow copy. Yes, exactly, Noel. It's because it's a shallow copy. That means that rather than copying the values, we just copied the position where both x and y are pointing to. We're not really changing those values. We're only changing what x and y are referencing to. So if we go ahead and say, oh, we're going to change this number to, say, 25, which is what we did, I think. Both x and y have that number modified. That's the difference between a shallow copy and a deep copy. A deep copy would go in and create a clone, and it would do 6, 8, 5, 12, 13, and let's delete this other member. Let's put it as 20. If this was a deep copy, then x would point to this one, and y would point to this one. So we would make an exact replica of the array, and then only one would be modified. So how do we make then that deep copy and that shallow copy? Well, this is where we go back to loops. And the one that is excellent for arrays because it has a built-in counter is the for loop. So we did for z int z equals 1, it equals 0 until z, or while z is less than x dot length. That meaning that we're building the new int x dot length. So this is how we're essentially building that clone. We would then increment by 1, C++, and then we do y z at the index of z equals x at the index of z, and then we modify that, and then we do system out just to debug that. And now because we force that copy, if we debug, stop and rerun, first of all, to begin with, you see that there are two different elements saying that it's pointing at int 5 at 790 as opposed to the same one, and this value is different than this one. Now we were able to only modify one. This is a deep copy of the same array. Okay, so now that we understand then an array and a shallow copy, you can see how I am referencing the array elements by saying what is the offset. Again, when I was talking about the offset and the jumps, that's how you read and write values. If I want to read the value, let's say y1 and then x1, where I'm performing a read operator on the first jump on the array 1 and on the first jump on the array y. So I'm going to compare both values, x versus 25. You can see how I am reading those values, and here using the same the same mechanism of the square brackets I'm writing to it. So strings are very similar to arrays, but strings are a little bit more special because at some point in Java, since it borrows a lot from C++ and C, the simplest way to write text would be to make a char array or a character array. So if you guys remember, a char is a primitive that represents a single character. So in Java, we have the string literal of the single quote. That means that it's by a char. And if we use double quotes, that means that it's a string. So Java has those shortcuts to represent a character and a string. If we wanted to build a string, or the way that they used to do it in C and C++, is that it would have a char array, where you would have an array represented by all these, where it would have a null character at the very end, and then whatever text on the cell. So if we would say Java 1, we would put it all in that string. And that's basically how strings were in the beginning in C and C++. But Java decided to take it one step further. What happens if you have a char array wrapped by an object with a bunch of functions, convenience functions, that would allow you to manipulate and perform certain operations on strings? For example, putting two strings together, which is a concatenation. Or for example, checking if a string begins with another string. So a way that you can create a string is by using this double quotes, or you can do the new string and then pass either a string or say new string and pass a char array. Or so there's many ways to initialize a string, and I'm going to show you more about those. If we want to understand better what is in a string, we can go into Google and put Java String API. In this documentation, you can see all the constructors, all the ways to build a string, a bunch of different functions on the string, like to see if we can copy a string, or to test if a string ends with another string, or formatting a string, or trying to find a substring, like finding out if a string belongs in another string, or there's so many operations as a convenience function. Because strings have a char array, all the inside of it, all the considerations of arrays apply to a string, plus some more. So meaning that if you want to modify a string, basically you're creating a new string rather than creating a new one. Strings, for performance reasons, you cannot also change the internal values of the same object. Strings also work with switch statements we were talking about, but also strings are not really a primitive. Meaning that if we do this, string name equals Juan Carlos, which is my name, and then we were to do this of that name, what this thing would represent is that the name Juan Carlos is an actual object that has all those values. Java might try to like optimize it, but it's an actual object that it's that string. So if we did then string name2 equals new string Juan Carlos, they would be different objects. So in other words, if I did this, and let's run it just so you see it, it would print false because these two guys are different objects. Now, if I wanted to compare the values on these two objects, I would use the method dot equals. The string object knows how to compare two strings. So now if I run this, the value is true because they're different objects. It's just like essentially, I don't know if you guys know the Olsen twins, but it's like saying, do they look the same? And this means, do they look the same? Yes, but are they the same? No. You know, like any twins, that identical twins, do they look the same? Yes, but are they the same? No. It's the same thing here. We have two different objects, two different living things. They're not the same object. They're not the same place in memory. In this case, if we go back to our whiteboard and try to represent that string, we would have a string here and a string here. Are they the same object? They're not the same object. They're not the same. They have the same values. Because of that, then we understand that strings are unmutable. In a lot of languages, this was something introduced in Java later in the game. It was not in the original version of Java. And it is because a lot of languages like Python, JavaScript, things like that have built-in ways to run through iterators. So let's assume that we have an array of strings, and let's say it's going to be names, and we're going to be putting Peter, we're going to put John, we're going to put, well, let's actually put the Beatles. John, Paul, George, and Ringo. So we have some names. The way that we would iterate things that are if we wanted to print all these names, it would be quite inconvenient to do something like this, which is basically what we did. We create a pointer where we're going to be saying names.length and then x++. If we wanted to then say string name equals names x and then name. So what this thing is doing is that it's creating a new reference to that list on the array and printing it in that list. So there's one extra step in here. If you can see, this entire loop is 3 lines. So other languages have introduced a way of doing a better shortcut or something more readable, where you can say string name in this colon does in names and then name. And let me just print another separator here, so that way you can see that both are going to do the exact same thing. And let me make it a little bit bigger. So you have John, Paul, George, and Ringo with this method. And then we have John, Paul, George, and Ringo with this method. You can see that here I am not referencing in any way the X. I didn't have to create the variable. I didn't have to assign it. I didn't have to create another variable. It all does it for me, which is really convenient. Now we're going to go into our little sorting exercise. Basically, we're going to iterate over the array on a 2 by 2 number basis. So these two and then these two, etc. So we're going to say for int x equals 1. Notice that I'm starting at 1 because I want the 36 to be the first one. And why is that? Because if I start with x equals 1 and then continue until the end, I can then do int first equals ages x, and actually x minus 1, because that would bring it down to 0. And then the second would be, so now I have two numbers to compare. So if I do this guy, let's just print the system out and then do first and then concatenate. To concatenate a string, we use the plus sign. Or to put two strings together, we use a plus sign. And if I did that, then I'm going to start comparing 24 versus 36, then 36 versus 14, then 14 versus 35, 35 versus 22, etc. until we're done at 25. So this is how I'm grabbing two numbers, right? Then I can say if the first is smaller than the second, then we are going to swap those numbers. That means that if we did a manual run on this, 24, 36, 14, 35, 22, 37, 42, and 25. So we're going to grab these two and we're going to be, okay, should I swap these numbers just to make sure that I put the first one in the beginning? The answer is going to be no, because 24 is smaller than 36. So right now, in the scope of what I'm comparing, 24, these two guys don't need to be swapped. In the second one, when we would hit 36 versus 14, we would need to swap, because the first one, which is 36, is going to be bigger than the second one, which is 14. So we are going to then swap these values. So then we're going to say, we're going to create a temp, and we're going to say that equals second. And then we are going to say ages x equals ages 1. We're swapping those numbers, or let's say first, to put it that way. And then ages this guy equals the temp one. Actually, we can even say second, because we're not referencing. So we're switching. In this case, second was ages x, and then x minus 1 was that. So if I was going to print the array, when I get to this first pass, you're gonna see that the first time that I did it, it swapped this 36 and 14, it swapped those. And then it continued swapping until, the next iteration, it just grabbed 36 and 35, it swapped these two. Then the next iteration, between these, it swapped these two, which, you can see it on the next one. Then on the next iteration, it didn't swap anything. Then on the next iteration, it didn't swap anything. And then on the next iteration, it didn't swap anything. We went from the beginning until the end swapping numbers. The array is not completely sorted, because we still have these 24 and 14 and these 25 all the way down here. We're going to go through the entire array, sorting or swapping as much as possible, but we're going to add one variable. Sorry. I swapped, and I'm putting just this ridiculous name so that it's readable for you guys. And we assume that we're not swapping. And then if we swap, then we say, well, have I swapped equals true, because when we did swap, we are swapping those values. But at the end of the day, even at the end of my algorithm, even if I am keeping track when I have swapped, I've only done this thing one time to know I'm not done. At the very end, I'll just know when this thing happens. And actually, let me just even put it here. Have I swapped? And then have I swapped? So now if I run this guy, at the end of it, I get the same array and saying, yes, I did swap. So now I know that I did swap, and the array is incomplete, or potentially incomplete, because I swapped in the last time. So I will know that once I go through all these numbers without swapping, that's when I know that I am done with sorting this array. The requirement for us to know that we're done with sorting the array is when we have essentially gone through the entire array and not swapped any numbers. So this is where the do while becomes really key, because we're going to repeat this process while I have not swapped. But every time that we start the process, we're going to test if it hasn't been swapped. So for every time, so for example, the next time that we're going to consider this as if it was a new array. So 24 and 14 needs to be swapped. Then so on. So let's just run this guy. Now we have this array, 14, 22, 24, 25, 35, 36, 37, and 42. And we realize that we have not swapped. Know again that the control variable that is telling us if we're done or not, and we gotta keep doing it until we're done, it is this have I swapped flag.